Okay, so now let's get a little deeper into the notion of a test bench and how we can actually understand what's happening in a test bench, right? A test bench is just like any other piece of Verilog code, right? Except that its purpose is to explicitly provide a stimulus to the design under test, right, which is usually called the DUT. Some people also refer to it as the DUT, just sort of pronouncing it as a word, but it's the design under test, and that's the important thing that you need to keep in mind. So we need to provide stimulus to this DUT and verify that it is working correctly. What this means is that the test bench by itself is self-contained. It has to generate inputs to the DUT, observe the outputs coming from the DUT, but apart from that, by itself the test bench does not have any other inputs or outputs. Okay. In particular, it does not have any ports. It might have inputs in the sense that it might actually read something from a file or do something else, but it does not have ports. It is not meant to be instantiated somewhere else. Okay. So the basic structure of a test bench basically looks like this. I need to instantiate the DUT inside the Verilog code. I need to generate the stimulus and finally monitor the responses. Here's an example of what that looks like, right? As you can see, it starts off with this keyword module and then a name. The important thing is it doesn't have these parentheses after the name which tell it there are ports. A test bench does not have ports, right? You then declare the variables that are going to be used for the connections with the DUT. Like I said, reg and wire have very specific meanings. Reg is for things that are typically going to be inputs to your DUT. You want to be able to assign values to them inside your test bench. Wire is usually for things that are coming back from the DUT. You want to be able to monitor them, but you do not plan to sort of assign values to them out here. They are going to be assigned inside your DUT. So that's step one. You basically declare the values or declare the signals, names. After that, you instantiate the DUT, right? And the way you do this is basically you have this thing, this my underscore and is the name of your module, right, that you are trying to test. And this second word after that DUT is actually an instance name. Why do we give it an instance name? Because I can actually take this my and module and have multiple copies of it in here, right, with different sets of inputs and different sets of outputs usually, right. Think of it like you have a breadboard and you have multiple different inverter chips. You can put each one of them, they all behave exactly the same, but because they are getting different inputs, they are going to show you different outputs. This is exactly what's happening, and in order to reference something on the breadboard, you would probably, well, use some kind of a label or some name associated with each of those individual chips. That's exactly what this label out here is doing. It's something that you get to choose, you can put in anything that you want, and finally it allows you to map all the inputs and outputs. Once we have done that, you actually apply the stimulus and monitor the output. This by itself is a fairly complicated task. We'll be talking a lot more about it with examples later. Now, like I said, modern test bench templates, system Verilog, the biggest difference you would see is basically that reg is gone, wire is gone. I've replaced both with logic, right? It's just used to sort of simplify things a little bit. I would strongly suggest you use this unless there is a very specific reason not to. So just once again, talking a little bit about reg and wire versus logic. The original notion of Verilog used two different keywords, reg and wire. Wire was used for connections and reg is used for so-called procedural updates. That is to say, when I want to assign a value inside an always or an initial block. And like I said, the important thing is that a reg does not necessarily correspond to a physical register. This is a common source of confusion. Please be very clear about it. There is no guarantee that something declared as reg in Verilog actually becomes a register or a flip-flop. In system Verilog, they simplified that. They just brought in one keyword, logic. It can be used for either input or output, and interestingly, it can actually automatically infer the direction, whether it's an input or an output, by sort of looking at the signal flow, right? So the idea in Verilog that you need to explicitly make a difference between something that can be assigned or something that is going to get a value from a DUT, well, it turns out that the compiler is actually pretty good at figuring that out for itself, right? So system Verilog simplified it. Now, a couple of notes on compatibility. As I said, If you are using the word logic, you do need a compiler or a simulator for Verilog that has system Verilog support. And yes, this is easily available in EDA Playground. More importantly, it's available in, for example, the iVerilog simulator, which is what we are using on EDA Playground and which is open source and you can install on your own systems for running your code. The problem is you are likely to come across legacy code at some point that still uses reg and wire extensively. So you need to be aware of what these are and what the implications are of declaring something that way. Alright, so the one part of the test bench that we sort of just brushed aside when we started out was this business of how do we actually do stimulus generation. And now you can see that there is this fairly large block, right, which starts with this keyword initial. Now initial, as the name suggests, is basically something which says when the system starts up, okay. And like I said, Verilog has this notion of time associated with it. So initial, you can think of it as something which basically runs at time 0, okay. Good, that's one good way of thinking about it. You have a begin and end which allow you to sort of define the scope of that initial block. And inside that we can, for example, do things like assigning values to inputs a equal to 0, b equal to 0. Then comes the tricky part. We have this notion of hash 10, and what this hash 10 says is wait for 10 time units. We will be talking a lot more about what these time units are and so on a little bit later, but the important thing is, you remember I told you that initial runs at time 0 when the system starts. Well, how can I wait for 10 time units? It turns out that initial just starts at time 0. The time at this point when it just enters the block is time 0. I can then tell it to wait for time units. It will basically pause, let the rest of your systems, if you have the DUT and various other modules, advance their internal notion of time until they have got to 10 time units, then come back here and continue. What that means is, by having a equal to 0, b equal to 0 out here and then having a hash 10 and then saying a equal to 1, I can actually wait for 10 time units and then change the value of a throughout my entire simulation, right. This change in a will be seen by all other modules outside the initial block as well. They will immediately start responding to changes that are made inside the initial block. I wait for another 10 time units, make b equal to 1. Once again, blocks that are outside, such as the DUT, will look at the changed value of b and respond if necessary, right. So this notion that there are delays is a very important part of simulation in Verilog, right, and it allows us to sort of create an entire story, a sequence of steps that the test bench is going through. At the end, there is this keyword called $finish. You will see that it starts with the dollar sign and it basically is the word finish. One other thing, as you might notice, pretty much every statement out here ends with a semicolon, just like in a language like C, okay, and unlike Python, for example. So Verilog is not white space sensitive, it is case sensitive. So for example, capital initial, capital begin and so on would result in errors, unlike VHDL, which is not case sensitive, right, all kinds of potential sources of confusion there. But the bottom line is this $finish over here is what's called a system task. It's not directly a keyword of the language, it is something which tells the simulator, okay, finish up with the simulation, wind up everything and stop, okay. There are other kinds of system tasks as well. One of them is what's called the $display system task. The $display is interesting. It basically says that anywhere in a procedural block, you can actually have a $display, and when the code reaches the position of that procedural code, it will run this $display and actually cause it to, it's like a printf statement. It will print whatever value is out here, okay. The interesting thing is a $display would actually explicitly need to be put in either here or here and so on, and only when you are going through this procedural block and you hit a $display, it will cause that to run. You cannot have a $display out here outside the initial block. It has to be inside either an initial or an always block. There is a related term called the $monitor, which is interesting in its own way. It's something that you don't have an equivalent for in a language like C. You can also have an initial inside, or rather a $monitor inside an initial block, but it does something much more interesting. What it says is, once I have given a dollar monitor statement out here, any time that A, B or Y change, it will trigger this printf statement and cause all of this to get printed out. Okay. You can see that there are format specifications, for example, %B for binary, %H for hexadecimal, %D for decimal and so on, similar to the printf in C but not exactly. For example, hex is different. There is a notion of time that can get printed out, right. The interesting thing out here is that, yeah, I mean, this can be used for printing certain values and monitoring the results. What the dollar monitor does is, once you have declared it, any change in A, B or Y at any point in time later will trigger this dollar monitor once again. You don't need to go in and explicitly sort of put display statements everywhere that you make a change. So it's good for debugging in the sense that any time a signal changes, it immediately prints it out for you and shows you that something has changed. Yeah. So as you might imagine, dollar display and dollar monitor do not actually have physical meaning. If you are trying to model gates or logic or something like that, they are used for tracing and debugging. They are somewhat limited compared to what you can do with C, but on the other hand, they do have this notion of time, which is crucial for debugging Verilog code. So let's put everything together, right, and try and run through a full simulation out here. Effectively what we have is, we first create a DUT as a module. In our case, we are going to declare it as this my and. It has two inputs, A and B, and inside, right, we basically have this assignment statement, which for now we just call it an assignment statement. What it means is just that it runs through, performs this computation anytime A or B change and updates the value of Y. I want to test this. For that, what do? I first need to declare the signals. I need to instantiate my DUT. I set up a initial block to do the monitoring. And as you can see, I can have multiple initial blocks. My second initial block is the one that actually does the stimulus generation. It says give a set of values, wait for some time, give a set of values, wait for some time, give a set of values, wait for some time, and so on. Finally, display this test complete and finish. Okay. What do you think a simulator is going to do with this? Well, it's going to know that by looking at these two pieces of code, it knows that this ends up inside this. Therefore, this is the top level module. It compiles it into some intermediate format and then starts sort of going through, creates space for having these values, creates an instance of this, sets this thing up, sets up the initial, and at this point in time it says, okay, time is equal to 0, let's proceed. Starts off by assigning certain values, waits for a certain amount of time after that. The entire simulation sort of pauses and then sees, are there any other events, anything else that needs to be handled? Okay, no, fine, let's move on to the next one, which is A equal to 0, B equal to 1, and proceed that way step by step until the entire simulation is complete. So here on EDA Playground, I have exactly the same test bench that I talked about. As you can see on the right hand side, I have this my and gate has been declared. The left hand side has my test bench. It basically has the registers and wire that are used for the inputs and output. I instantiate the DUT. You can see that I have directly put in, by the way, this notation that you see over here is what's called the named port mapping, right. In general, unless you have a very specific reason, and the only specific reason that is acceptable is that there are certain built-in primitive gates in Verilog which are AND, OR, NOT and XOR, I believe. Those do not have named port instantiation. For anything else, any module that you write, you should use explicit named instantiation like this. The alternative would have actually been that you could have also written code which just did this, right, where I do not have the names, I just basically give the order of connections. This will also work, but don't do it, right. As a rule of thumb, this is not the correct way to write code. Now, why is it is a problem? Because if you look more closely at this, if for some reason you get the order wrong, or later you, let's say, add another signal out here, right, maybe if I went in and added a new signal, or if I changed the order out here and basically made this as y comma a comma b, right, for whatever reason, maybe I changed the order of inputs and outputs in my actual module declaration, this is wrong, this is just plain wrong, right. But if I do this, for example, where I have dot y of y dot a of a and dot b of b, this still works. Even though the order that I have put in here is different from the order in which they were declared, it's still going to work perfectly fine. Okay. Alright, so now you have that, and once we have got the DUT declared out here, let's go in there. We have set up the monitor for debugging values, and I also have this thing where I test all the possible combinations. What happens when I click on run? Internally, the iVerilog compiler, so to say, is actually going through and converting all of this Verilog code into some kind of intermediate format, and then, like I said, it sets up the simulation at time 0. It goes through, checks all the initial blocks, decides what needs to be done, assigns a set of values out there, runs the code for that, then sees there are no further events or changes in signals, advance time by 10 time units, see what happens at time equal to 10, right, set a equal to 0, b equal to 1, and so on. Okay. All of that happens very quickly once I click on this run. It goes through the compilation process, runs everything that we have out here, and finally comes up with certain set of results. Now the time that it takes for actually compiling and running the results could vary. EDA Playground is a shared resource. There are multiple, it's basically a freely available resource, which means that they need to figure out when they can allocate compilation resources for you. In general, if you install iVerilog on your own system and run it over there, it should be fairly fast. Now let's quickly look at the results. What you can see is there are a whole lot of statements that got printed out, right? But I had only one display statement out here. So where did all these things come from? Well, they came from this $monitor, right? And as you can see, any time that A or B or Y changed, it had gone and printed something out. Okay. You will also notice that it doesn't sort of make a difference between A changing, B changing, Y changing. It sort of clubs everything together at time equal to 0 and prints all those values. In reality, as we will see later, there is actually a difference in the times when each of these things changes. But it's something that you need to, for now, just go with this, that the $monitor looks at a particular time, sees all the changes and prints them out. At time equal to 0, these values were given in, then 10 time units passed and A became 0, B became 1, which is why we see that at time equal to 10, A equal to 0, B equal to 1 is being shown. Then move further, time equal to 20, it's 1, 0, and time equal to 30, it's 1, 1. At that point, I finally get to this test complete and finish, right? $finish called at time 40, right? And it basically terminates the entire simulation. So this is basically the set of steps that a complete Verilog simulation is going through. So there are a few important things that you need to remember, right? If you are using reg and wire, then the inputs to a DUT are reg in a test bench. In general, the outputs from a DUT are wires in the test bench because they are being driven by the DUT, right? So this is again a notion. The word drive is something that you will keep coming across when you are talking about hardware. We essentially say that if I have, let's say, a gate like this, right, with two inputs A, B and an output Y, Y is driven by the AND gate. This A is driven by some source out here, and B is also driven by some source out here. B drives this AND gate, A drives this AND gate, right? The output of the AND gate drives something else. Okay. So there is this notion of a particular signal driving, or rather a particular gate driving a signal to a value of 0 or 1. Okay. It forces it, it pushes it towards either 0 or 1. In this case, what we can say is the value at Y is being driven by this AND gate. the value at A and B are not driven by the AND gate. The AND gate does not have any influence on what the values of A and B are, right. So, this notion of drive is important to understand a lot of why you need registers and wires and so on. What we are saying is the outputs from a DUT are driven by the DUT, right. That is the whole reason why we call them the outputs of the DUT. And as far as the test bench is concerned, they are not something that the test bench is allowed to change the value of, because the DUT is the one controlling that. So, if I declare it as a reg, the idea is I am going to change it inside the test bench. I do not want to do that, so I declare them as wires. Once again, system Verilog makes life a bit easier. It will figure out for you automatically whether this is being driven or is being driven by the test bench or by the DUT, and figure out whether it is an input or output appropriately. $monitor is useful for continuous value tracking, $display is useful for specific messages, and at the end of a simulation you want to include the $finish. Interestingly, if you don't, you will actually find that the system sort of goes into an infinite loop. It keeps on advancing time waiting for something to happen. You might argue that that's a bit silly. Doesn't it know that there are no further statements out there? Well, that's not how a simulation works, right? Simulations are sort of waiting for something to happen at some future point in time. So, they continuously keep advancing time to see when the next event is going to happen. And as you saw in the previous test case, we gave something like 10 time units between the stimuli, changing the value of AB, right. Some meaningful values need to be given there, but as we will see later, you have to be very careful with what kind of interpretation you assign to this, because it does not actually correspond to physical delays.